Hello world, my name is Victor Engelmann. Welcome back to my channel. In the last video I showed you how to debug the Linux kernel, and in this video I finally want to start digging into the code of the Linux kernel really. Now, before I start I want to show you this book here, Linux Kernel Development by Robert Love. And yeah, that's a really good book. I've learned a lot in that book, and this is actually very rare. In my experience, there are really not many good resources out there to get into kernel programming. And yeah, this is one book that is actually really good. It's pretty old. It's, I think, from 2010. And it mainly discusses the 2.6 kernel, which was a very landmark kernel at the time, and yeah, if you find older kernels today, maybe in IoT devices or something, they typically are 2.6 kernels, because that was really a very important point. A lot of features that we still have today in the Linux kernel were added in the 2.6 kernel. Like, for example, I think the completely fair O of 1 scheduler was added in 2.6, I think. But again, a lot of stuff is still very much the same, so it's still a relevant book. And yeah, the stuff that isn't the same, well, you'll still be able to find out what's going on. It's still a really good book that will really help you get into the code. And yeah, but one thing I want to tell you is you have to read that book cover to cover. You cannot just flip through it and pick the topics that you're interested in. That won't work. You really have to read it cover to cover. Okay, so today I want to talk about interrupts. And yeah, what are interrupts? Interrupts is a way for an operating system to communicate with the hardware. I mean, when an operating system wants to do something, like a user space program has told the kernel, hey, I want to open a file, for example, well, then the kernel has to talk to a driver, and the driver then sends out some code to the hardware, to the hard drive, telling it, hey, give me this or that sector. Okay, now a hard drive, for example, is really slow. So you wouldn't want to pause at that moment and wait for the data to come back, you know, because that would be really a long time compared to what the kernel can, or what the processor can do in the meantime. So so what you would want to do at that point is just send out the command, hey, give me the data, and then go on doing something else. Okay, but then what if the data comes? Okay, what do you do when the hard drive is done fetching the data? Well, that is exactly what interrupts are for. So when the hard drive is then done fetching the data, it would issue a so-called interrupt. So how that works is you have an interrupt controller, for example, an advanced programmable interrupt controller. You have this interrupt controller and you have your CPU, your processor. Okay, and the hard drive is connected to the interrupt controller, and yeah, when the hard drive is done fetching the data, it tells the interrupt controller, and the interrupt controller has one line, one connection to the CPU, to one pin here. Now, when the hard drive is done fetching the data, it will tell the interrupt controller in whatever way. We don't need to care about that. And yeah, then the interrupt controller will put voltage on this connection to the CPU. And yeah, the CPU is then hardwired to, when there's voltage on this one pin, what the CPU then will do is it will stop doing what it is currently doing, okay, and instead look into a so-called interrupt descriptor table. Okay, and this interrupt descriptor table, IDT is a very common shorthand for that. So this interrupt descriptor table is inside the RAM. The kernel has to write that into the RAM, and as part of the startup process, it issues a command to the CPU telling it, hey, this here is your interrupt descriptor table. And yeah, that just has a list of IDs, so-called interrupts, 1, 2, 3, 4, and so on. And associated with these IDs are just some memory addresses. 0x, whatever. And these are function pointers, okay, for functions that don't have a parameter, so void functions, if you will. So when the CPU receives the signal from the interrupt controller, it then fetches an ID from this interrupt controller. For example, ID 0 is for the timer. You have a clock on your machine, and every, I think, 1 millisecond it issues a timer interrupt. And yeah, that is ID 0. And yeah, what the CPU then does is it just jumps to that location. So you have to put some machine code there, and yeah, put the location of that machine code into this interrupt descriptor table. So for example, you will have a handler for timer interrupts, and the address of that you will put into this table for ID 0. Okay, so when the timer interrupt comes, the CPU stops doing what it's doing. It stops executing Chrome or whatever user space application you're running currently, and it will look into the interrupt descriptor table and jump to this location. Okay. For example, it will update the clock in the corner of your screen, or well, a timer interrupt will also cause the scheduler to look, hey, should I switch to a different task, and stuff like that. So stuff that has to happen periodically would be done by the timer interrupt. And yeah, when it's done handling the interrupt, then it will return. There's actually a separate assembler command IRET to return from the interrupt, and that also frees the connection to the interrupt controller. So that also tells the interrupt controller, hey, I'm done, you can now resume sending interrupts. Right, so while I'm handling the interrupt controller is deactivated and will not send more interrupts. Now, if the interrupt handler here does anything, it will probably overwrite some of the registers of your CPU. Right? I mean, this is code, and code just changes registers. Like when it does some computations, for example, that changes registers. So when you return back to the user space program, that would be very problematic if you had just changed the registers, right? Because now you have something in there that the program doesn't expect, that would mess up what the previous program was doing if it now had different data in the registers than before. So what the interrupt handlers typically will do is they will push all the registers and so they are on a stack. Then you handle the stuff. It typically will be done with a function call, and when that returns, you pop all the registers back to restore them. In opposite order. Okay, now, as I said, while the CPU is processing an interrupt, the interrupt controller is deactivated, so it doesn't send more interrupts. And that is a really bad thing, because imagine you have, for example, a network card and you get a lot of data through that network card. Maybe you're doing a download or whatever, and you get gigabytes of data, and every packet causes an interrupt. Then imagine the handler for that interrupt was really, really slow, right? Then the network chip can receive some data from the network, but they will typically have very small buffers. So it can buffer a little bit, but if the interrupt handler is really slow, then you just get more data than you can handle in that time. And at some point the buffer will be full, and then the network chip will just have to refuse to take more data from the network. Okay, and then you'll get some network slowdown, something like a network congestion or something like that, and that's a really bad thing. So what you want to do is you want to free up the interrupt controller as fast as possible, right? So that you can then get more data from the network, maybe process that on a different processor even. We have multiple processor machines today, but if you just did it like this, then you would get one packet, handle it, return. Get the next packet, handle it, return. Get the next packet, handle it, return. And that would mean that all the packets would be handled sequentially. But again, that's not what you want. You don't want the interrupt handler to take a long time. You want to free up the interrupt controller as fast as possible. And that's why interrupt handling is split into two parts, so-called top half and bottom half. So the top half just fetches the data. So the top half is what you have in the interrupt descriptor table. So if data comes from some device, then the top half in the interrupt descriptor table will just fetch that data, but not process it yet. It will just put it into some queue or something, because, the queues that you can use inside your RAM, you have a lot of RAM, okay? You can put a lot of data in there, but your devices typically don't have a lot of buffer, so they cannot store a lot there. So you would take the data from the device, put it in a queue, and then already return from the interrupt, so to free the interrupt controller. Okay, so and then you would do the actual processing of the data from that queue later, and that is then called the bottom half. There are multiple ways how you can tell the Linux kernel to do something later. We will discuss that in the next video. Today I want to talk about the top half primarily. So this mechanism that when the hardware sends a notification, the CPU reacts to it and then returns to its previous stuff. Okay, so this is what we will do today, and let's jump right in. So I'm again in this busybox directory as in the video about kernel debugging. So here is a kernel, an initial RAM drive, and this start VM script, which runs QEMU with this kernel, the BZ image, this initial RAM drive, the init.rd image, which contains the busybox and nothing else, and runs this inside the current console. And this here was for debugging, so this makes QEMU run a GDB server. And I think last time this is what I had done to debug, to run a debug session in GDB, the GNU debugger, where I put I connected to that GDB server that QEMU starts, and sets 2 breakpoints and then starts the machine, because this -S makes QEMU wait for a connection before it really starts running in the GDB server. And this here then told that GDB server to really start the machine. And this VM Linux file is where GDB pulls the its symbol table, because in this BZ image the symbol table is stripped, so it's not there anymore, and because of that we use that as this VM Linux file here as the source for the symbol table. Okay, so this is how I did it last time. In the meantime, I've switched the program to debug. So I'm using KDBG. The acronyms in the debugging world are really insane. Like you have GDB, KDBG, KGDB. It's really a mess. But KDBG is a KDE application named KDBG for debugging. I'm also telling it to connect to the GDB server and to pull its symbol table from the same file. But you don't set the breakpoints through the parameters here. So I'll run this now. Okay. And this is what KDBG looks like. It tries to connect, I think, to the executable that I've told it, but that executable isn't running, right? It's that's just a file for the symbol table. I think KDBG just doesn't understand that and opens this program here for program output. But I'll just close this. This is what KDBG looks like. I'm not super happy with it, but it gets the job done. So I really haven't found an ideal program for debugging the Linux kernel yet. But this is okay. So compared to GDB, this is the advantage that you can set different hotkeys for run, step into, step over, and step out, and that's something that you need all the time. So I think it's a good thing to have hotkeys for that, and it is just better at navigating source codes and stuff, better than GDB. So I've connected to the VM, but the VM is still paused because of the -S. It's waiting for me to tell it to start running. And you do that with the run command here with this button. But we haven't set any breakpoints yet, so start kernel. So this is also something that I like. When you set a breakpoint, it tells you where in the source codes that breakpoint is. So start kernel is in init main, line 936. I think that's good to know. If you are looking for a file that contains a certain function, then yeah, you can set a breakpoint for that function, and yeah, then this program will tell you where in your source tree you can find that function. So that is a good thing. Okay, run. And yeah, as with the GDB debugging we did last time, we immediately hit this breakpoint at start kernel. And yeah, now it starts doing stuff. Okay, now interrupts. Let's go to source Linux, and in here the interrupt handling is architecture specific, so this code will be in arc, and then the architecture you're using, in my case it's x86 kernel, and here we have idt.c. Remember, IDT was shorthand for interrupt descriptor table. And here this idt.c is an important file for this. Here we have, which line is this? Here, this is the interrupt descriptor table that the kernel then gives to the processor. So this here is really the object that the kernel builds and then fills with the entries, and yeah, it's called IDT table. It's an array with IDT entries. And yeah, every entry in that table is a gate descriptor. Now, what is this data type gate descriptor? That is in arc x86 include asm descriptor definitions.h. And in here we have this type def, which sets this data type gate descriptor here to the data type gate struct. Okay, and that's right above it. So this gate struct, this is really the data structure that is put into this table. And yeah, if you remember my video about interrupt descriptor tables in the WYOOS operating system, this structure is a complete mess, right? This dates back to 16-bit days. So here you only have 16 bits for the address of the handler, but then that was when they moved to 32 bits and then to 64 bits, they couldn't just add stuff to it. I mean, the processors couldn't just increase this to 32 bits, for example, because that would break the backwards compatibility to the old operating systems, right? And they wanted old operating systems to still be able to run on the new processors, right? So what they did instead is they just added more bits at the end of the structure, and so these 16 bits plus these 16 bits makes 32 bits, and then when they switch to 64 bits, right, this, see here, if def 64 bits, then they add another 30 bits on top, and then the actual 64-bit address is all over the place, right? I think the last 16 bits are at the beginning of the table, and then the next 16 bits are somewhere in the middle of the table, and then the high bits are at the end of the table. It's a complete mess, but what you want to do, that's stuff you see a lot when you're dealing with hardware, and in backwards compatibility of hardware, that's not unusual. So this is what the table looks like. Of course, you cannot just set an address, you cannot just throw an address in here and expect that to work, right? Because the address has to be put into different places. And for that, there is argx86 include asm desk.h, and in here we have a function called packGate. Okay, and this packGate gets one of these gate objects and fills it. So here this unsigned long function is the function pointer to the interrupt handler, and this is exactly what I told you. It just takes the bottom 16 bits and puts them into offset low. Here it sets some flags in this bits object. Then from this function it shifts the function by 16, making the next 16 bits the lowest 16 bits, and then it just takes these 16 bits and puts them into offset middle. And if we are in 64-bit mode, then we also shift the function by a 32-bit, making the highest 32-bit now the lowest 32-bit, and then it takes these 32 bits and puts them into offset high. Yeah, that's awful, right? And I think I was wrong. It doesn't even put the interrupt numbers into the table. It only puts the addresses into the table. So why? I mean, it makes sense. Why would you put the ID into the table? It's really just the index of the object is the number that it would be in. This is actually done down here. The number is then in here in native write IDT entry, which gets the entire interrupt descriptor table as an array, as a parameter, and then in that array it goes to the entryth index, and there puts this gate descriptor, right? So with packGate, it fills this gate descriptor and then mem copies that into the interrupt descriptor table. And yeah, when it is done writing this table, it then calls load IDT, which, yeah, here is just macro defined to a function called native load IDT. And yeah, then native load IDT is a function which every architecture has to have an implementation for, so that the linker finds something for this native load IDT, right? This kind of is a bit like polymorphism, right? It's this is kind of like the virtual base function, and the different architectures override that, but yeah, you only ever have one architecture when you compile, so you don't really need to make that explicit. Yeah, which native load IDT is used just in the end depends on which architecture's object files you link into your kernel, right? So another architecture would then have a different native load IDT function in a different object file. Okay, and yeah, in this x86 we have this native load IDT here. So yeah, x86 gives native load IDT as just the assembler command LIDT. And yeah, if you remember my video about the interrupt descriptor table in the WYOOS video series, this is exactly what I did there, right? I created an interrupt descriptor table and then also issued the assembler command load IDT. And yeah, this here passes the pointer to the table, right? It gets a pointer to the table and then here uses that pointer as a parameter to this load IDT. Okay, so this really tells the processor, this is the location of my IDT. And yeah, when everything is set up, then well, if you have given the processor the interrupt descriptor table, it won't start. It still won't start servicing the interrupts until you until you tell it to start serving the interrupts. So that is done in argx86 include asm IRQ flags.h. Yeah, here we have this native IRQ enable, which does an STI start interrupts, and yeah, CLI disables them. Okay, now let's look at this in the debugger. Well, we've seen this native write IDT entry, right? So I will put a breakpoint there and start running. And yeah, look at that. Last time I told you nonsense because I said that start kernel was where the kernel started running, but we have a breakpoint on start kernel, and now we have hit a breakpoint before we hit the start kernel breakpoint. So this is actually happening before start kernel, right? And if we look into this, This is here something called secondary startup 64. And here's an x86-64 start kernel, which obviously must run before the start kernel. Okay, and okay, here it says something like IDT set up early handlers, which sets some handlers for exceptions. So if something in the boot process does, let's say, a division by 0, then you wouldn't want the whole machine to crash. You would want to handle that in some way. And so this sets some handlers here using this setInterGate. And setInterGate takes the interrupt number and the handler address, puts that into an IDT data object, and IDT data, that's also in desk devs. So here this is also where we had the gate descriptor. Right here we had gate descriptor was gate structure, and there's also IDT data, which contains the number for the interrupt and the address, plus some flags and some infos for the memory. One such object is then populated with the interrupt number and the handler address, right? And then from there it is copied into the IDT table in IDT setup from table, which size is 1, so it copies only one entry from this IDT data array to the final gate descriptor IDT. Okay, and for that it creates a gate descriptor object, fills it with the data from this IDT data object, and then goes to write IDT entry, which then does the actual mem copy into the final array, right? Not really elegant if you ask me, but whatever. Okay, now this is running in a loop, so if I would now just continue, it will just hit the same breakpoint a few times. Now to prevent that from happening, I will disable the breakpoint temporarily and now step out of the function and step out of these functions and here step over this loop. So here we iterate through the loop 28, 29, 30, 31, 32, and now it's done with this loop and now goes to load IDT. Step into, and what do we see here? This asm volatile load IDT. So that's what I've shown you. Okay, now we are out of that, and now I will re-enable the breakpoint to find the next location where the IDT is edited. So now that I've re-enabled the breakpoint, I will continue running. Now we hit the start kernel, but that's not the breakpoint we are looking for, so continue. And okay, now we've hit it again with from start kernel going through setup arc, which makes sense because every separate architecture should then provide its own setup arg function. You know, the way polymorphism is done here. Not real polymorphism, but yeah, if you only have one architecture here, then it kind of works like polymorphism. And here we have IDT set up early traps. Okay, 2 entries here, and yeah, it does the same thing, right? It has some IDT data objects. Then here has one gate descriptor, and yeah, then yeah, fills this gate descriptor object here with the data from IDT data, and I'm pretty sure that we'll use this pack gate. In fact, let's look into this. Step into IDT init descriptor. Okay, it doesn't actually use this pack gate. But that is functionally the same thing, right? It's a different function, but it basically does the same thing. So, okay. Okay, so this IDT setup early traps is the next location where we set IDT entries. Now I will disable the breakpoint again and yeah, step out. Again, load IDT, step out, setup arc. Now enable the breakpoint again and continue. Okay, we are still in setup arc, but now IDT setup early PF. I don't know what. Page fault handler. Okay. Okay, why not? That also sets one entry. Yeah, for the page fault handler, I bet. And yeah, that is then again copied to the IDT. Okay. Let's continue. Disable the breakpoint. Step out. Re-enable the breakpoint. Continue. Okay, now we are not in setup arc anymore. Here we are now in trap init. But this is still architecture dependent. Okay, setup traps. Def IDTs. I think that's probably something, another table where you have some entries that are then copied here. So yeah, size 19, so there must be 19 entries in this def IDTs table, which must then be an array of IDT data objects, which are then copied into the IDT. Again, disable the breakpoint. Step out. Re-enable the breakpoint. Continue. And now we are in native init IRQ. Again, architecture dependent. And yeah, I can tell you this is the last time this breakpoint would hit. Yeah, here, set up advanced programmable interrupt controller and IRQ gates. Set up from table 16 entries that are copied into the table. Okay, now again, this native init IRQ is the last time we go into this native write IDT entry. So now I will set a breakpoint to native IRQ enable. Yep. Okay, it took a while. Now I have 2 breakpoints there. Okay. Okay, now I have a breakpoint there, and yeah, this one I will disable again. Continue, and yeah, native IRQ enable. So the table is now finished. It's loaded, and now we want to start servicing the IRQs. Native IRQ enable comes from arc local IRQ enable. In arc x86 include asm IRQ flags 80. And yeah, that's coming directly from start kernel, local IRQ enable. Okay, so that part, this local IRQ enable coming directly from start kernel, then starts servicing the interrupts. And yeah, so this is how the interrupt descriptor table is built in the Linux kernel. I actually wanted to do some more stuff in this video, but yeah, this video is long enough now. So yeah, we will talk about how drivers can then hook into that interrupt system in the next video, because this really took much longer than I expected. So, but I think this is a good point to stop here. So yeah, this is how the interrupt descriptor table is built, and yeah, I really think it's really cool to finally get into the source code of Linux and see some actual code in action and debug this stuff. And yeah, I'm quite happy with this right now. And yeah, if you are happy too, if you like this video, like it, share it, subscribe, and see you next time.